Greetings and welcome, internet friends. Mr. Waddy here, reviewing a little bit for the Chapter 3 geometry test, in which we're dealing a lot with parallel and perpendicular lines and the proving whether or not angles were congruent or supplementary, or whether lines were parallel if I knew certain facts about angles. So let's jump right in. This is the review assignment from Big Ideas. Here's question 1. Let's see. Think of each sketch in the figure as part of a line. Which lines or planes appear fit the description? So lines perpendicular to QR. So here's QR, and if I want lines perpendicular to QR, I could use NR, right? NR. I could use PQ. This appears that these are right angles if this is a rectangular prism, rectangular prism. So I also could actually have used LMR. So lots of possibilities. And they did want all of them. Which lines? Yeah, plural. Lines. So that appears to be all of them, that given line. Now, those aren't the only ones that would be. Those are just the only ones that are drawn. So how about this one? How about lines skew to QR? So skew lines don't intersect. You might think, well, oh, so they're parallel? No, not necessarily. They exist on different planes. Parallel lines don't intersect on the same. So for instance, ML is parallel to QR, but they share this plane, right? Or NP is parallel to QR, but they share this. So ones that are skew, like JM and AL, and I know I'm just throwing segments on this. I'm trying to save time. Arrows. And then also JN here. And you could also name these segments. All right, so that's a kind of vocabulary check right there. So here we go. How about this? Find the values of x and y. So notice that in this problem, I already know that these lines are parallels. And so if I know these lines are parallel, that means I could use theorems like the corresponding angles theorem. I could use theorems like the alternate interior angles, height, right? Alternate exterior angles theorem, or consecutive interior angle theorem. Bam. And these three all have the conclusion that if lines are parallel, then the angles, right, cut by the transversal, that all of these kinds of angles will be congruent, well as consecutive interior angles will supplement, add to one. So that all is true. Also, you can always use vertical angles, linear pair postulate as well. So let's see what I can say here. So let's see. They didn't necessarily. You don't necessarily have to find x before y, but you could have. So here we go. Let's say I want to find angle x here. Sure, it's a linear pair with this y expression, but let's see if I can relate it to something that isn't going to bring another variable into the picture. And in doing so, I can realize that the 48 and 5x minus 17 are alternate interior angles. This is true by alternate interior angles theorem. So find the values of x and y, and I'll add, for my sake, and y. Oh, Mr. Watty. So here we go. Let's solve this. Actually, I'm gonna speed solve this. Add 17 to both sides, says the guy who now is gonna try to figure out math in his head. Let's see. 58 plus 7, 65, right? And then divide both sides by 5. So 12, 13. So that's the value of x. And now if I want to find y, sure, I could use linear pair postulate, say that it adds to 180 with this angle. But I think I can actually use an even easier route. I realize that these two angles are consecutive interior. So I know that y plus 48 is equal to 180. I'm not setting them congruent, but this is by consecutive interior angles theorem, the only one in which they are supplementary. And then if I subtract 48 from both sides, it looks like I would end up getting 100. Nope. Well, 132 for y. All right. Which, yes, and y also ends up being. All right, over here, even faster if I can. I can find x first, not necessarily the case, but x and this angle are alternate exterior angles. So I could say that those two things are, so I could set their measures equal by def of Cong, if I'm not mistaken. So consecutive interior angles theorem is the one that did the grunt work there. Sure, I could also have compared these two as being a linear pair. All right, so there are multiple approaches there. And just because these other angles aren't labeled doesn't mean you can't use them. If you happen to see an alternative route and can justify your work, I'll gladly give you the credit. It just might, sometimes it might take a longer way. Subtract 32 from both sides. Oh, dear. Man. And then divide both sides by 6. I get 14. So correct me in the comments. Right? But here we go, focusing on the geometria today. And then let's see, to find angle y, this angle here is a linear pair with x angle. Technically, I also could have found this angle over here and then use corresponding angles theorem between those two. That one's probably a little easier, so let's do that. So to find the linear pair here, I'll just do 180. Got it. So what's that going to be? 4. And then the 5y minus 21 is going to equal 64. In this approach, it was true. So you also could have said these two things add up to 180 and plugged in 4 for x. Substitution there, and these were a linear. So multiple approaches. 5y equals like 85. Then divide both sides by 5 and add. Right? So that is a use of the theorems. Now, the theorems all have the hypothesis if parallel, right? If parallel, then these things are true. And let's jump into the world of the converses, in which here I do not know parallelity. I'm unsure of those things, but I'm trying to figure out what value of x would make those lines parallel. And so in order to do that, I would use the converses. Corresponding angles converse says if corresponding angles are congruent, then the lines are parallel. Or alternate interior angles converse. If those angles are congruent, then the lines are parallel. Similar to this, right? And kayak. Except this one says if consecutive interior angles are supplementary, then the lines are parallel. So the hypothesis and conclusion are swapped for these. I use converses to prove parallelity. Well, I use the theorem ones already knowing parallelity, and I use the something about angle. All right, so that's the subtle difference there. You're well aware of that. Looks like I'm going to need to label some additional angles here because I don't have a name for these kind of angles. But, well, I'll tell you what. This 3x is corresponding with that. So those two are congruent by... Ooh. I was just about to apply a theorem. That's only true... Okay, all right. If the lines are parallel, which is what I'm trying to prove, then these two angles would have to be congruent. All right, so I'm still kind of working my way there. I'm going to end up setting these two things as supplemental in a moment, but I did it by corresponding angles now there. So if these lines are going to be parallel, the value of x that makes that true would have to be one in which those two add to 180. Say 3x plus 2x plus 20 equals 180. And this isn't true by a theorem. This is true by, I guess, kind of assumption. I'm saying this is what would need to be true in order for them to be parallel. All right. So I could then combine like terms. 3x's and 2x's is 5x plus 20. 80, subtract 20 from both sides, and I would get 60, and then I would get x equals 32 after dividing by 5. And then if I found x was equal to 32, I could then say m is parallel to n by, well, actually, I guess I was resting most strongly upon the corresponding angle's converse there. They didn't ask for a y, but that's kind of what I ended up doing. I also could have technically worked with this supplement and corresponded those two. But yeah, that's actually a tricky problem because they ended up not giving you angles that were in either of those relationships. Over here, a little bit easier. These two angles are in corresponding positions. And if those two angles are congruent, then the lines will be parallel. So in order to find the value of x that makes them parallel, those two things. So 7x minus 11 is going to equal 4x plus 58. And let's subtract 4x from both sides. I'm cruising through the algebra here, I realize. Not showing the intermediate steps. But this is for my geometry students. I assume that you are solid algebraticians. But remember, you could always go practice algebra, watch my other videos, Khan Academy, all sorts of reasons. Add 11 to both sides. 3x is going to equal 69, and then divide both sides by 3, like 20 value that will be. And when x is 23, then I could say m is parallel to n by the corresponding angles converse. They didn't ask for y. I'm just having us practice those. In this chapter, you are going to need to be able to do proofs using. All right, determine which lines, if any, must be parallel. All right, so let's see. I've got both of these are perpendicular to the same line. So x, y are parallel. Actually, I just realized I'm filming this ahead of time. I don't have the name of that theorem memorized off the top of my head, folks. But the idea is this: two lines perpendicular to the same line will be parallel to each other. Yeah, I don't remember the name of that, but I'll write it out. Two lines perpendicular to the same line are perpendicular, or will be parallel to each other. And I don't remember the name, so guess I have to do the grunt work of proving it another way to you, don't I? So these two angles are a linear pair. That doesn't rely on parallelity. So those are both right angles. Both add to 180. If one of them is 90 by def of right angle, subtract 90, both sides. You end up finding out that this angle is 90 as well. And right angles congruence theorem says that all right angles are congruent. So that means these two angles are. Those two angles are in corresponding positions. So I could say that these two angles end up being are in corresponding positions. If they're congruent, then the lines are parallel by the corresponding angles converse. So it takes a little bit more work for me to do it that way. I realize I did it verbally for most of it, rather than using the name of the theorem. But I want to point out, if I forget the name of a theorem, I could always reprove it, which is actually what I just did. All right, let's see what's going on in this sketch. All right, so I have A is perpendicular to N and perpendicular to N. So I'm going to say A is parallel to B for this as that, right? Actually, you know what? Tell you what. Internet friends, you guys can fast forward. I've got my theorem. I've got the official name. I'm screenshotting it. I happen to have my notes. Another one of my 100 tabs. So here we go. This is the official name of that theorem. Two lines perpendicular to a transversal theorem. There we go. So what could I abbreviate that as? As the LP DT? or the LP little L'Pitat. There we go. That's why I never remember that name, because it's a long one. But if two lines are perpendicular to the same line, then they're parallel to each other in a plane. So A and B are parallel by the L'Pitat. And let's see, do I have any? So I know, let's see if I could go for this. Now, I know C perpendicular to M. I don't know if it's perpendicular to N, so I don't think I have a way of proving M and N. Ooh. Guys, out. C is perpendicular to M, and B... Yeah, I guess the issue is here with C and M is that they could have been drawn like this, right, and still have had their own perpendicularity, but it's unrelated to the others. I can't get it to jump to the other side. Yep, yeah, we tried though. We tried. All right, let's see. This last problem, tricky one. I'm skipping a bunch. This one. It requires a whole bunch of steps, but this is the idea. I'm trying to find the distance from a point to the line. And so I'm going to need to do a whole bunch of work. This relies a lot on your old algebra. But here I've got a point and a line. So step one, which is going to be quite a bit of work, I'm going to find the line perpendicular through the point. Okay, so that's my step one that I'm going to do. So in order to do that, I'm going to take their line, I'll call it y sub 1, why not, equals half x plus 1. Notice the slope of their line is the half. And therefore, if my line's going to be perpendicular, the slope of my line is the opposite reciprocal of that. So this one's positive, the opposite would be negative. This one is 1 over 2, the reciprocal would be 2 over 1. I can rewrite that as just simply negative 2. All right, so I know that my line that is perpendicular to this one that passes through this point will have a slope of 2. Now, this line, I want to point out, does have a y-intercept of 1. However, I am not interested in, it's unlikely, it's possible, but unlikely, that the two lines will have the same y-intercept. That would require two perpendicular lines to intersect at the y-axis. And it's possible, but, right, there's also infinitely many lines that don't do that. And so I can't just assume that my line is going to have B2, equal to 1. I don't know what B2 is. So here's the other strategy. I'm going to use the form y equals mx plus b. You also could use point slope form to do this, which is y minus y1 equals m parentheses x minus x1. And I'm going to plug in what I know and solve for what I don't. So what I'm going to do is I'm going to use this as an x1, y1 situation. I know a point. I know the slope. I'm going to plug in, right, what I know. So I'm going to plug in 3 for the y. Here we go. I'll plug in negative 2 for the x. I'll plug in negative 2 for the m. And I'm going to solve for b, right? So I plug in what I know, and I solve for what I don't. So I've got 3 equals negative 2 times negative 2 is positive 4 plus b. Subtract 4 from both sides. I'd get negative 1 equals b, and we'll flip it around. b equals negative 1. So now that I've got my slope and y-intercept, that is like the DNA of any line that makes it distinct from other lines. And so now I can write the equation of my line. Y2, we'll call it, equals negative 2x minus 1. So I just did, yes, only step 1. So step 2, all right, my goal, remember, is I'm trying to find the distance between this point and that line. The shortest distance is going to be perpendicular to that line. Hence my finding, right, perpendicular right there. I'll do it down. Step 2. In order to find the distance between the point and the line, I need to have the point where the two lines intersect. So find the intersection. And to do this, right, we've got a variety of ways to do these things. I can use elimination, substitution, graphing. So my first line that they gave us was y equals 1/2 x plus 1. My line was y equals negative 2x minus 1. I guess I'm going to scroll out these ones because in this world, if I'm finding the intersection, those y's are the same, right? So I've got to solve a system of equations. You can do so graphically, but I'm not a fan of graphically. It sometimes can take a lot of time, and it may not be the most accurate if it intersects at a non-lattice point, somewhere not on the grid. So to solve this, let's say, let's do substitution. Both of these are already solved for y. So I'm going to take this and plug it in here for the other equation for y. So 1/2 x plus 1 equals negative 2x minus 1. Easiest way to deal with fractions is to kill them off by multiplying both sides by the least common denominator, which there's only one denominator here, 2. So 2 times 1/2 is a full x. 2 times 1 is 2. 2 times negative 2x is negative 4x. 2 times negative 1 is negative 2. Let's add 4x to both sides. 5x plus 2. Subtract 2 from both sides. I'd get 5x equals negative 4. Oh, fraction. And that's going to be rough. Divide both sides by 5. I get negative 4/5. This problem's going to be beast. All right, but we've got calculators, etc. So I found x, which is, right, one of the coordinates of the intersection. Let's find y. So to find y, I can now plug this into any of my original equations. Let's do that. Plugging in part is why it's called substitution. I'll plug it into the one with the positives. I'm a positive person. If you don't remember the steps of substitution, you might need to go back to Chapter 5 in Algebra 1. It's often Chapter 5 in those books. Not always. And so I'm going to plug in for x, my newly found x, right? So negative 4/5, bam. And so I'll have y equals negative 4/10 plus 1, is I can reduce this fraction, negative 2/5. And to write 1 with a common denominator, that's 5/5. I'm finding coordinates, so really at some point it just makes sense to use decimals, but get an exact answer. Actually, even our decimals are going to be exact in the world. Negative 2 plus 5 is 3. That means my intersection is negative 4/5, comma 5th. All right, so that's my intersection. That's also the same as negative 0.8, comma 0.8 if you're. All right, the last move, last step, because I'm trying to find the distance, right? Right now I've got the intersection between a perpendicular line and the given line. So I've got to find the distance. Point. And in order to do that, we would use b equals the square root of x2 minus x1 squared plus y2 y1 squared, right? And so my 2 points now, I've got 2 points, is negative 0.8, comma 0.6, and I've got my given point. I've already forgotten what it was. Negative 2, comma 3. Negative 2, comma 3. There's my 2 points. I could label those as x1, y1, and x2, y2, although it won't matter too much. And I would get distance equals square root of 0.8 minus all squared plus y2 minus y1. So 0.6 minus all squared. I'm probably going to start reaching the calculator. Becomes minus a negative becomes plus. So that's 2 minus 0.8. I get 1.2 squared plus 0.6 minus 3, it's going to be negative. That minus sign is going to be dealt with by the squaring in a second. 3 minus 0.6, I believe it's 1.2 squared, I believe it's 1.44. 2.4 squared, I'm going to grab a calculator here. 5.76. Add 1.4, get 7.2. And a decimal approximation of the distance is square root of, so I get approximately, is the distance from that point to line. Hopefully I didn't make any errors in there, but the general process is the same nonetheless. I find a perpendicular line, I find the intersection, and then I find the distance between my intersection and the given. All right, well, thanks for watching, Internet friends. I hope you all have